Happy Wednesday. Hope everyone is doing all right and stay dry on the way into class. We have a few announcements today, and then we're going to continue on and mostly finish up with action potentials. I don't know if you can tell, I love action potentials. I think they're amazing. So hopefully we'll gain an appreciation for them. Just a reminder, 4 days of lecture left. Final exam 2 weeks from Friday. Friday, May 13th at 7:30 a.m. 2 hours. Cumulative exam worth 25% of your grade, so don't blow it off. Anything we've covered so far is fair game. The exam will take the similar structure. It'll just be about twice as long. Well, questions?
Will the test itself be twice as long as well?
The test itself will be twice as long. Right? So it's a 2-hour window. The exam will be, I think, about 250 points. Your normal exams are 125. It's the final. All right, it's a true cumulative final. So go back and remind yourself what we've learned the rest of the semester. Midterm exam number 4, your last one. You have the Friday for point adjustments. I think that we have got most of the issues taken care of at this point. If you still have questions, feel free to come and talk to me. I have office hours right after class today. If you can't make those, email me and I'll do my best to schedule another time to meet with you. As far as let's see here. So the TIs are going to offer a review, just like for all the exams. They're going to do a final review. That will be next Tuesday, 5 to 6 p.m. Feel free to take anything you're still confused about as far as questions to recitation this week. You can certainly start going over final review then, but they'll be having a separate session Tuesday, 5 to 6 through the normal time. I'm working on a room. Hope it will be in here, but I will let you know once that's confirmed. So there is a chance to review. Because we're at the end of finals week, that comes way ahead of your finals, so that's plenty of time to fill in any holes that you might still have issues with as far as concepts. Okay? And then the final announcement today. It's that time of year, course evaluations. eCafe is now available. Just like the midterm review, if I get a certain percentage of response, I will give you guys an additional few extra credit points. Those will be tacked on to your midterm, whatever your midterm total is. Okay? 4 points if 85% of you send me an eCafe response by the time I figure out grades. You got lots of time. Encourage all your friends to do it. I really do want to hear what you think about the course, what you think works for you, what didn't work for you, right? So that I can help to continue to improve this course. Yes, question? Do the eCafe for the lab as well. That's a separate section number, so do for both. Those are sort of 2 different components of this course. Do the lecture one specifically to evaluate this lecture course, do the lab one specifically to evaluate the lab, and how you thought that went, what could be improved, what you liked. Don't just tell me what didn't work, tell me what worked for you as well, okay? So that we can continue to improve this course as I continue to teach it, okay? Any questions over that? All right, pretty straightforward. All you have to do is send me an eCafe response and tell me what you think. I'll keep you updated next week as to where the response level is, so you know how hard to start buzzing your friends to get that eCafe filled out. All right, any other questions before we get started? All right, let's keep going with action potentials. action potential. See, excitatory cells. You guys should be pretty excited about this. We had just finished, I think, on Monday, what exactly an action potential was. It's that change in membrane potential as different channels open and close in the membrane, typically in the membrane of a neuron. We divided that action potential up into separate stages or separate phases. The resting state, the depolarizing phase, the repolarizing phase, the undershoot or hyperpolarization phase, and the resting state. And I'm going to clarify today, ask me a question, so I'm going to clarify what the difference between repolarizing is and hyperpolarizing. All right, but first, let's see where you're at as far as understanding what's driving the generation of this action potential. So we're going to say follow the dot. All right, right now we're talking specifically about sodium channels. Let's think about when they open and close and what their state is at different points in our action potential. All right, so at the yellow dot, what state are the sodium channels in? All right, remember we talked about when these channels were opening and closing?
Pardon?
What's driving those differences? Everyone get a chance to answer? Take a look. So when our membranes are in this first phase, this resting phase, our sodium channels are closed. The sodium is not moving across the membrane. What about there? What's the state of the sodium channels at that point in our action potential? Talk it over with your neighbors. Remember what open and closed refers to versus activated and de-inactivated?
So yeah. Well, I just want to know where 40 is. Activated. Yeah, because it's not either 40. Oh, 40 is 40. Is it? Positive 40 is the very negative 40 is the
Everybody has a chance to answer. Let's take a look. Little more confusion here. So, what does that black dotted line represent? Threshold potential. Are we above that yet?
No.
So what's the state of the sodium channels? They're still closed. Oh. Right, you have to get past that threshold to trigger opening of that sodium channel. Aha, yes.
So that the little rise is just the charge moving across.
So that's the charge that's moving, passively moving across from upstream in the cell. All right, it has to build up enough sodium to get past that threshold to trigger opening of the sodium channels. So that's incoming signal
Once the charge reaches above the charge.
to that part of the membrane. What about there? What's the state of our sodium channels?
in the bottom. At the line, right? When they goes down, when they go to line. I'm not sure. Okay.
All right, everyone get their answers in. This one, I think we'll have figured out. Take a look. All right, so at that point, we're above that threshold value. Our sodium channel's opened up. What about there? What's going on with our sodium channel?
Because it's inactive. So it's
Alright, what's going on with our sodium channels? Coming back down the other side of our potential.
no, the last.
Give you one more second. Take a look. The answer's in. All right. Correct. It is inactivated. So remember, when we get to about the top of that peak, about 40 millivolts, positive 40 millivolts, that inactivates our sodium channel. That means that ball and chain plugs the hole. So inactivated means the gate is open. Well, the gate can be either opened or closed, but the ball and chain is plugging up the channel. Right, so open and closed refers to the gate. Activated, de-inactivated refers to the state of that ball and chain and whether it's plugging the channel or not. So it's inactivated at that point. What about there?
Because the bomb is being activated.
What happens at that point?
Yeah, she was mentioning that. Is there 5 feet?
What is the color line? All right, everyone get their answers in? Take a look. All right, a little bit more confusion here. So at the last point, we were inactivated. When does the sodium channel become de-inactivated? Negative 65. And even though I haven't shown you the scale on this, what is this solid line here? Our resting membrane potential. What millivolts is that? Negative 60. So where does the sodium channel become de-inactivated?
Under that point.
Under that point, at negative 65. All right, so it is still just inactivated.
What?
All right, we haven't hit the point at which that ball and chain drops out. Yeah, question.
Will there ever be a point where it closes again? Or,
Closes the gate.
yeah. Or is it still always inactivated after it drops below the threshold?
So once it drops below the threshold, it both de-inactivates and closes the gate. At this point, it doesn't matter what state the gate is in because it's inactivated, meaning that channel is plugged. You're still looking confused.
So is it possible to be because you said it's still.
Well, it doesn't close the gate. So at negative 65, once we get below that resting membrane potential, you both close the gate and de-inactivate. So you reset completely.
So it doesn't close below 40. When it drops below 40, minus 40.
Ooh, that's a good question. I'm not actually entirely sure when the gate closes. That's a good question. I don't know the exact point at which that gate closes. I will look that up and let you know. It sort of doesn't matter because it's still inactivated. So the state of the gate doesn't affect whether or not sodium is moving through the channel, right? Is everyone clear on that? Or is everyone still confused? Okay, so we were inactivated at this point still. All right, what about here? What's going on with their sodium channel? Take a look. Okay, here is the point where we become de-inactivated. So that ball and chain drops out of the channel. What did I do? Sorry, ignore that. All right, one last one. What happens at this point? At the previous point, we de-inactivated. We're back at resting membrane potential. What's the state of the sodium channel? Everyone get their answers in? Let's take a look. All right, good. We're back to just being, we've reset the protein, we're back to being closed. All right, so that is the sodium channel. What about the potassium channel?
We don't need to do this.
Okay, remember that action potential is generated by the opening and closing of sodium and potassium. So let's look at potassium. We figured out sodium. Everyone get their answers in? Take a look. All right, a little bit of confusion. At this point, our potassium channels are closed. What about here? channel, think about what we talked about on Monday regarding the way that potassium works relative to sodium.
It's okay, no, everything I choose to.
All right, let's take a look. Right, they're still closed. All right, potassium channels are still waking up. What about here?
I was actually thinking of just not operated since they were fancy. People are too confident. They die every time. Oh, so it's the opposite of size.
All right, so let's take a look.
Remind me of your mic.
All right, so we're a little unsure where those potassium channels are opening up. They are still closed here. All right, potassium channels are sluggish. They're slow. They don't open up nearly as quickly as the sodium channels. What about here?
I left my notebook in the car too. Today's not my day.
Get your answers in. I'll take a look. All right. Let's see what you think. All right. Finally, our potassium channels are open. So they don't open up, all right, until we hit this peak, and that's what's driving the drop in our potential. One last question, in case you haven't been paying attention to this part of it. What's the time frame over which these action potentials happen?
Wait, what's up? I'm so excited. Yeah. But like, no,
All right, get your answers in. Let's take a look. The time frame of the action potential. All right, a little bit of confusion. It happens on the order of milliseconds. Okay? So fairly quickly, but not as quickly as some of those others. Options. All right, so here's what you need to know. All right, you need to know the time scale of those action potentials. You need to know each one of the stages. So resting, depolarization, repolarization, this undershoot or hyperpolarization back to resting. And you need to know in each one of those what the state of the sodium and the potassium channels are. So make sure you understand that series of questions we just went through. As far as the time scale of the opening and closing of the potassium and sodium channels, so we talked about that sodium channels open quickly. So they open quickly, have that huge influx, and then they close. The potassium channels are slow. They open more slowly, they close more slowly. So potassium is driving that depolarization. Potassium is driving that repolarization to hyperpolarization, and then slowly back to, once they close, back to resting membrane potential. So they have different response kinetics as the channels. All right. So one last thing regarding this. We've talked about depolarization phase, repolarization phase, hyperpolarization phase. What's the difference between repolarization and hyperpolarization? The membrane in both cases is going more negative. Why do we make a distinction? Past the resting membrane potential.
One's going to normal, one's going too far.
Right, so one is returning back. So repolarization, you're coming back down to the state you started at, that resting membrane potential. Hyperpolarization, you shoot past it. All right, so we're using that resting membrane potential as our baseline. Repolarization is coming back down to that baseline. Hyperpolarization is going beyond it. All right, so this is when we have the potassium channels still open while the sodium channels are inactivated. Once the potassium channels start to close, the de-inactivated sodium channels are a little bit leaky, so that helps bring our membrane potential back to resting. All right, so that is the ins and outs of what generates an action potential, but that's just one action potential. That does not get us a signal from the dendrites of a neuron to the synaptic termini. All right, we talked about the buildup and passive spread of ions in that cell body. So it gets the axon hook, it passes that threshold, and then we get the propagation of action potential. So it doesn't just generate one, it's got to generate enough action potentials to get all the way down that axon. So we need to talk a little bit about how propagation is happening. We know that at the axon hillock is where we trigger an action potential, and what triggers the next one, and the next one, and the next one. So when we're talking about action potential propagation, we're triggering action potentials in a wave down the membrane of that axon. So there are a couple of things we need to think about. First of all, once a segment of membrane has fired, right, generated that action potential, how soon can that same segment of membrane generate a new or a second action potential? So I want you to think about this for a few minutes. Based on when things are happening in that action potential and the state of the sodium and potassium channels, there's a period in that action potential where you cannot initiate a new or second action potential. And then there's a different phase where it is difficult but not impossible. So think about what we just talked about. I'm going to give you a few minutes to talk to each other. See if you can figure out what part of this action potential we cannot generate a new action potential during, and which part can we generate a new action potential. Everyone's looking like they have no idea what I'm talking about. Think about the state of the sodium channel. All right? How do we initiate an action potential? What state is that sodium channel in? And then think about the changes of state across the action potential.
I don't really get the yeah. Repolarizing, repolarizing, repolarizing. You're trying to get back to the rest of
Actually, enough.
at the peak. So when it is depolarizing.
All right. Everyone had a chance to discuss that? Anyone think they have it figured out? Let's go through it together. All right, so we know that at resting potential, a membrane can be triggered to fire an action potential. So it can fire one, and then once it has returned to that resting potential, no problem firing another, as long as we pass that threshold value. What about if we move that same stimulus a bit earlier? Will this stimulus generate a new action potential? No. Why not? It's below the threshold. What about this one? Hasn't hit threshold. What about this one? Yes. All right, what's the state of the sodium channel at this point? We have de-inactivated it. That ball and chain has dropped out of the channel, which means that it's reset. If the gate opens, then sodium can move across that channel and generate a new action potential. So the difference being that in order to get there from this hyperpolarization phase, the stimulus has to be about twice as large. It has to be huge. So that's why it is possible to fire a second action potential in that hyperpolarization phase, but it's difficult because you have to have a huge stimulus. You have to have a huge change in that membrane potential. So this part of the action potential, this hyperpolarization phase, it's difficult but possible to fire a second action potential. And we call this the relative refractory period. We can fire an action potential, but it's pretty difficult. So this relative refractory period happens. It's controlled by when that sodium channel is de-inactivated. So in that action potential, once the ball and chain falls out, it is possible but difficult to fire a second action potential. What about earlier in that original action potential? So we know this is possible. What if we move that stimulus up? All right, will the stimulus generate a new action potential? What's your question? Talk it over.
Maybe yes. Didn't we just say yes? Oh wait, no, but that was really slow. No. Sodium, because sodium has to start coming into the
it will not generate a new action potential.
That was what you said, the sodium.
Why can't it generate a new action potential? It's above the threshold. The channels are the sodium channels required for that depolarization are inactivated. So even if that gate is open, sodium isn't going to move across the membrane. So this period of the action potential, where we are repolarizing and the sodium channel is inactivated, that's our absolute refractory period. Doesn't matter how much you depolarize the membrane, it will not fire a second action potential. All right, so our absolute refractory period is this period of time that the sodium channel is inactivated in that repolarization phase of the action potential. Question or just correct? Okay.
So absolutely cannot have the
All right, and it's not until we get down to that hyperpolarization phase, we hit negative 65 millivolts, it's de-inactivated, and you enter the relative refractory period that you can generate a new action potential. All right, so where in the neuron does the action potential initiate? Where specifically in the neuron cell? The axon hillock. That's where we initiate our first action potential. Remember this figure? We have that passive spread of charge, and once it accumulates past the threshold at the axon hillock, we generate an action potential. This is in part driven by the distribution of sodium channels. There are very few sodium channels in the membranes around the cell body. There are a lot of sodium channels right here at that axon hillock and across the axon membrane. Once we generate that first axon at the axon hillock, then those action potentials are propagated down the axon to the synaptic terminals. All right. So how do we get from the axon hillock to the synaptic terminals? All right. All right, so we know this. We generate an action potential. We don't know this yet, do we? Why does the action potential only move in one direction? Why does it only go down the axon, not back? It's the refractory periods, right, that we just talked about. So I'll post a YouTube video on how these refractory periods are controlling the direction of propagation. But if you think about it, all right, we generate an action potential in a small segment of the membrane. That action potential is causing sodium ions to rush in, and the sodium ions are going to diffuse out from that section in both directions. But in one direction, sodium channels haven't been fired yet. In the other direction, they have. Right? So if we look at this traveling as a wave down that membrane, we have our sodium channels. When they're open, they generate flow across. So they depolarize that section of membrane. They're flowing in both directions, but ahead of that action potential, the sodium channels haven't been activated yet. They're closed and can be fired. Behind that, the sodium channels are in those refractory periods, so they can't be fired again. So sodium is diffusing out from that action potential in both directions along the membrane, but the sodium channels behind it can't be fired again because of that refractory period and the state of the sodium channel.